Okay, the topic for today is the noise behavior of the common source stage. And I immediately see an error that I've never seen before. It is a stationary noise model that we will discuss. Stationary means that the statistical properties do not change over time. So it means that our observation time is long enough to have all possible states observed. So this is the announcement that we used when we did the introduction in the of the complete program. We will study the noise behavior of the intrinsic CS state, so the noise behavior without source and source connected, and then we will study optimization for different source types. Let's start with the intrinsic CS stage, the stationary noise model for such a stage. I guess you had this before at some other lectures of device physics. Um, so the noise, what you see is a small signal model of the FET in some operating point, and added two noise sources, ID and IG. ID is the noise current associated with the drain current. It has a spectral density given by 4kT n, which is a substrate factor, gamma, which is some constant times gm, and there might be 1 over f noise involved, and that is expressed by a FL, a corner frequency of the 1 over f noise, and f 1 over f, so that it has 1 over f noise. Gamma equals 0.5 in weak inversion and about 2/3 in strong inversion. So we need a function. We can create a function with the inversion coefficient and make the spectrum a function of the inversion coefficient so that this gamma smoothly goes from 0.5 to 2/3. And this function would then look like this. For a 0, for very small, smaller than 1, you have 0.5. And for much larger than 1, which is a strong inversion, you have 2/3. That is expressed by this function. The corner frequency for 1 over f noise shows a relation with the ft of the transistor. And this relation is given in this expression that you see, in which kf is some process constant, which makes this whole constant that is there, kf times 3 pi divided by 4kt and gamma, a constant, a kind of process constant, and ft, a thing that depends on the inversion coefficient, as we have seen in the previous lecture. That's important. We will use this knowledge later on if we are going to optimize the noise behavior for a capacitive source, and we want to have a low corner frequency for the 1 over f noise. And this is especially interesting because it covers the design problem for the active antenna that we are going to do, because maybe some of you already looked at the specification for this active antenna, and then you might have discovered that there was more noise allowed at low frequencies than at high frequencies. And one of the sources of this extra low frequency noise might be this 1 over f noise. And there you have a design criterion for this corner frequency. So this kf is a process parameter and the dimension is joule. So this is what I already said, and very important to remember, the cutoff frequency for the 1 over f noise is proportional with ft. So if you want to have a very high ft, unfortunately, you also get a high corner frequency of the 1 over f noise, and a constant between it is set by the process. So let's go to the second source. The second source is IG, the current, the noise current associated with the DC gate current. Now, in many cases, we can ignore this source because the DC gate current IG is very low. And otherwise, it will be 2Q times this current, and it has its own 1 over F corner frequency. So I just introduced a new one, FLG, to represent a corner frequency of the 1 over F noise for the gate current. So the DC gate current is IG, this is corner frequency, but often this gate current is assumed zero. It can be in the order of femtoamperes or picoamperes for a larger FET, but it also depends, of course, on the oxide thickness and the temperature. So it's not always very clear that you can ignore it. Sometimes you have to account for it. So this is the stationary model of the FET with the physical origin of the noise sources. So one noise source associated with the DC drain current and one noise source associated with the DC gate current. What we want later on for design is we want to have a, let's say, signal to noise ratio according to specifications. It doesn't need to be the best, but it needs to be according to specifications. And you understand that the noise sources are maybe not in the place that is optimum for doing this design. So what we want to do in the next step is to make a model of the CS stage with equivalent input noise sources. Because if we have such a model and we know the properties of the source, we can already translate this into source referred noise contribution of the CS stage. And if we have the source referred noise contribution of the CS stage, we know about the deterioration of the signal to noise ratio due to this CS stage. And that is what we want for the design. Maybe we can set up design equations for that and design a low noise or sufficiently low noise solution for the CS stage. And that will be one of the exercises for the next, for this evening.